invariant with shift. So let's now move this to the graphs. And to motivate this, we're gonna take the time domain and we're gonna represent that using ring graphs. So first of all, what are ring graphs? Ring graphs are a essential or cycle graph, or another name for them is circular graphs, are graphs that consist of a single cycle. That means that every node in this graph is a part of this closed cycle. So one example you can see here in this figure, V0 is connected to Vn minus 1 and V1. V1 is connected to V0 and V1. The whole thing together is constructing a ring or cycle, and there is no other nodes in this graph. Now, what we want to show is to represent this time domain using this ring. So it means that we have a time domain which essentially has some periodic boundary conditions. So let's say that we have a signal defined in the time domain on points t0, t1, t2, to tn minus 1, and I'm showing the function f evaluated at each point using ft0 and so on and so forth. So now, what I can do now, if I want to represent this on a ring graph, is that I associate each of the time points, each of basically point in time, to one of the nodes in my ring graph. So I'm going to say that for time t, I'm going to have node vt. For time t2, I'm going to have node v2, and so on and so forth. Then what will happen is that our function is going to be represented on that graph, meaning that I will have a real value or essentially a value ft0 corresponding to node v0. I will have a value ft2 corresponding to node v2, so on and so forth. And there is no reason why we don't have t1 here. That's just a typo. So now, go ahead. Sorry.
This function periodic?
Yes. So the function, we are just considering the domain to be periodic. Yes. So the domain is periodic. So the function is defined on a periodic domain. Now let's say that we consider, instead of looking at it as a set of different data points, we're looking at this f as a vector. For instance, one-dimensional vector that is defined on our graph. That means that, so that's the way we're representing this signal on the graph. You can think about it, for instance, like an image, which is defined on a 2D grid. Each point on this image has a pixel value corresponding to each grid point, right? So you can think about it the same way. This is just a vector. Now, then you have an image, for instance, to n by n image that is represented on the graph. Now the same idea. We are representing a vector f on this graph, which has v essentially nodes, and it is a ring graph, a circular graph. So now we want to, after motivating why we want to represent our data on a graph, now we want to define shift and essentially difference on this ring graph or chain graph. So for a chain graph or ring graph, I can define the adjacency matrix as a circulant adjacency, where if j is equal to I plus 1, and this mode n just means that we're finding the remainder after division by n, because the boundaries are periodic. So then if that is true, we will have 1 at that point in our matrix, and everywhere else, every other element in our matrix is going to be 0. What that means is that, first of all, this is a directed graph. as you can see on the figure. So it is not symmetric. So our circulant adjacency is not symmetric. Now, using this, we can perform time shift, meaning that we can shift our data in the domain that we have, which we are representing time domain here. By applying this circulant adjacency matrix on our signal F, signal vector F. So it is just a matrix product so matrix vector product. We have AC multiplied by F, and that's going to give us a shifted essentially signal. What that means is that we have value F1 here. Now this is shifted by 1. That value now resides, F1 resides on node 2, because we have shifted that by 1. So our circulant adjacency matrix can represent shift operation in the circular graphs. Now, another way you can think about it is that by shifting, you're propagating information in our graph, and that propagation has a direction dictated by the direction of the edges of that graph. So we are propagating, when we say we are propagating it forward, forward is defined by the direction of the edges. So we can similarly define a Laplacian matrix for our chain graph or ring graph. And the way to do that is by writing I minus AC. Now, again, note that this is a directed graph. So the diagonal elements are not 2 because it doesn't have 2 neighbors. We're just considering either in neighbors or out neighbors in directed graph space of our application. And here we are doing the same. So for everyone, I think it's the same. So it's going to be I minus AC representing our circulant Laplacian matrix. Now, what we want to do with this Laplacian matrix is to perform difference operation on the chain graph. So we want to do the difference operation that we could do on the time domain. Now we redefine every single here on our ring graph, and then we want to perform difference. And the way to do that is not anymore with the difference operator that was defined on the time domain, is by our Laplace matrix. So multiplying by Laplacian matrix is gonna result in this relation ft minus ft plus 1 mod n, which means that t plus if we basically whatever the number is divided by, and the remainder is that. So the difference with its neighbor essentially is gonna be the result of this multiplication, and that's what we are looking for. That's our difference. So now, after defining these two, we are going to talk about convolution on chain graphs. So we can define similar to this basically for 2 operations, the shift operation and difference operation. We can apply this using some matrix multiplication. Let's say that I have some matrix QH that is representing our filter, and then I can multiply this matrix QH by my function F, F, our vector F, our signal data, whatever you call it, right? So I'm applying this matrix on this, and the output is going to give me the convolved output. So now I'm just assuming that I have some convolution matrix that is doing that for me. But this convolution matrix can't be any convolution and can't be any matrix. It should follow some rules in order for it to be able to perform convolution. First is to be shift equivariance. The second one is to be difference equivariant. So difference and shift equivariance can be represented as commutativity with respect to the corresponding operators. So the shift operator was shown by the adjacency matrix of our circular graph. So the circulant adjacency matrix was performing this. So if I want for my matrix QH to be equivariant with respect to this basically operator, it should be commutative with respect to the circulant adjacency. Now I'm going to define the same thing, same idea for the difference operation. So if I want my matrix QH to be equivariant with respect to this operation, difference operation on the circular graphs, it should be commutative, it should be able to commute with the Laplacian, the circulant Laplacian. That means that LCQH should be equal to QH LC, and both of them should have the same result. So now one can show that if I want to define such a matrix on a circular graph, on a chain graph or in a ring graph, that is basically is equivariant with respect to shift, it should be able to basically be equivariant with respect to the difference as well. It should be commutative with A and C, and we can construct that by constructing a QH that is in the form of a polynomial with respect to our circulant adjacency matrix. So that means that I can define my matrix QH as essentially sum of different powers of my circulant adjacency matrix. That means that it's a polynomial function of AC. Now, this is defined on the circulant graphs, and that's the idea that we're going to take, and we're going to redefine using that the essentially convolution matrices on arbitrary graphs. So we're going to say that if I want to define a convolution matrix on some arbitrary graph, the way to do that is by defining my function as a polynomial of the adjacency matrix of that graph, or a essentially polynomial with respect to the Laplacian matrix. For now, let's stick to the adjacency. So let's say that I write down my QH as sum of different powers of the adjacency matrix, where I is just showing a to the 0. And these alphas are the coefficients for this, that coefficients for expanding these into essentially this form. Now, if you remember, the adjacency matrix, different powers are just representing different hop neighborhoods of each node. So that means that when I have a 2-hop neighborhood, when I'm multiplying that by alpha 2, I'm regulating how powerful my essentially my nodes in radius 2, the ones that are on with basically the distance from them is 2 hops, are affecting my output results. So we're constructing an operator, and this operator is applying essentially different distance nodes to your node, right? So it's gathering information from different distance nodes, and that's regulated by these hyperparameters alpha. So let's say that I have a function f defined on some graph. So that means that this is a b-dimensional vector. Then if I apply a convolution QH on this function, that means that in the nodal domain, in the spatial domain, so we are not working with the spectral domain that we were discussing, the Fourier domain or anything like that for now. We're just talking about the nodal domain that we have worked so far in the previous lectures. So if I have this function and I apply this operation on that function, the output is information, the output is gathering information from different hop distances of that particular node for every node in that graph. And that's the way this operation QH, this convolution, is updating my input signal F, and it's returning some output signal, which is essentially supposed to be, for instance, the output of our filtering, right? So I think we're gonna move to the next topic. So let's take our 5-minute break now, and we'll restart after that.
That every convolution you can find the polynomial expansion exactly matches the operator or its approximation.
There's 2 people, no need for message.
So the this convolution operator, you can always find a polynomial expansion for it, or is it sometimes it's approximation of the.
So that's essentially the way you're trying to design that, right? This convolution operations, you're trying to design convolution operations that are doing such and such. So can you repeat your question one more time?
I mean, just, yeah, I mean, exactly, it's like for
It's
every convolution operator we design, we want the exact polynomial expansion such that we can write in.
So yeah, so it's essentially the other way around. We are designing that convolution. So you design the convolution. It's not that you had the convolution and now you're trying to find them. It's rather the opposite. You have this and you want to design your convolutional filter. And it basically, we will see basically more than that. Yes. How's the homework going?
So I understand those three equations, the three functions, the adjacency matrix and the 6 and the props. Like you give three.
Oh, you don't understand, okay,
I understand.
you do understand, okay.
Yeah, I understand. I just load the data and like print something. I understand what they're doing, but I couldn't figure out how to write those classes.
Okay.
Is there any like tutorials or?
So I'm, no one asked this, so I kind of forgot, but I can share I think the code that I provided, I basically worked on a month ago or so. The session that we worked on PyTorch, the code for that.
Yeah, I remember that.
I think that should have some class, or if not, yeah, we can look at some examples on Thursday's class. On how the classes are defined. Yeah. So yeah, I guess we can do that. We can Thursday we can just go over some examples on PyTorch, so that everyone is essentially on the same page. And yeah, how about everyone else? Seems everyone else is finished homework. Just a quick note that there is a small bug in the code on the generation of the signal. I basically corrected that. So if you go to get on line 39 of problem 1, there is a new line that you need to add to your code in order for that to work. I will send out an email for everyone, but I'm just reminding you that for now. Yeah. How about yours?
I'm putting my effort right now.
What?
I'm just putting my effort right now. I haven't fully go through it.
Okay.
Check notes. I haven't got any comments.
Yeah.
Do we need to use these three functions in the classes? Like, or it's just for
So the
the
functions.
predict?
The functions are for your training. You need to define classes, and then you need to train, and you need then to define. So it's like this, you have two classes. One is a GCN class, then you have a pooling class. You define these as general classes that you can call to construct a model.
Yeah.
Then you construct a model that is using a GCN layer, a pooling layer, a linear layer. And then during training, you train this model based off of the data that we load using SIG and basically the functions defined at the top. So the data is not a basically concern for anyone.
We like we train just on the data set or on those like functions you define to get the.
You find this on the data set. So you can see there is a loop in the problem.
Yes.
Right, and there I'm selecting every 10 essentially data points, and I'm training the model using every 10 data points for 200 epochs. So yeah, so you don't need to be worried about the data and how it is being called. You just need to be able to define the classes, define the model, and train the model. These are 3 steps that are needed.
Those 3 functions is to do the predict, the there's, I see in the training section,
Mhm.
like there is a line predict equals to model.
Mhm.
And then you have adjacency metrics and the SIGS functions.
Okay.
What does it do?
I mean, I mean, if you want, we can just discuss that after class.
Okay.
Yeah, in the office hours.
Okay.
Yeah, I can't answer on the fly. But okay. So, yeah, anyone else, if you guys had a question, you can just stop by during office hours. And yeah, so let's just look at an example the next session so that we make sure everyone has covered these topics. So. All right, so far we discussed defining some matrix that is performing convolution on this graph. We call that QH, and that was all on a circulant graph. And we say that this can be represented as an expansion into different powers of the adjacency matrix. And then we said that in order to extend this idea to general graphs, what we do is to essentially take the same idea and we say that any matrix that is operated, basically a convolution operator on some graph, should be a basically expansion into these different powers of the adjacency matrix. So if now we want to apply some convolution on some function f, we can just write it as QH, our matrix, multiplied by f, our vector, which defines data on that graph. And that means that I'm gonna apply alpha 0 I times f plus alpha 1 a f, and so on and so forth. And if you think about it, at each of these, you are multiplying a different power of the adjacency matrix to our f. So you're gathering information from different hop distances from each node to update the value of that node. And when you sum these, what you're gonna do is to gather all information from different hops up to n hop distance of each node. And then we have hyperparameters alpha that are controlling the influence of each distance, the influence that each distance has on a given node Vi. So the reason that we wrote it this way was because we said that if we want this to be commutative with respect to the shift operation, we can write it, and the difference operation, we can write this as a basically polynomial function of the adjacency matrix of the circulant graph. But when we extend this to the general graphs, this idea is not necessarily true, this statement. So it's not necessarily true that if I write this as a polynomial of the adjacency matrix, it is commutative with respect to the difference operator as well. So therefore, you can write your function essentially as a basically polynomial function of either adjacency matrix or Laplacian or some variant of this. So for instance, let's say that we can use normalized adjacency, or we can use normalized Laplacian matrix, where these are symmetric normalizations, where we mean that by symmetric, we mean that we're dividing each basically element aij by degree of I and degree of j. So in the matrix form, you're multiplying d to the minus 1/2 on both sides of the matrix, be it Laplacian matrix or the adjacency matrix. So now So there are multiple matrices that we can select. We can select adjacency, we can select Laplacian, we can select their symmetric variants. So the question is which one? And there is no definite answer for this. It is all depending on the application that you're dealing with. And this application, so you need to have a trade-off between pros and cons of these basically models. So for the symmetric ones, one interesting property is that the eigenvalues of these are bounded, which results in stability. So for instance, the Laplacian matrix is basically its spectrum, the set of its eigenvalues has a minimum 0 and a maximum 2 at most. And that maximum 2 only occurs if you have a bipartite graph. Other than that, the largest eigenvalue is always less than 2. The second property, which is very desirable based off our conversation, is that for symmetric versions, if you define the convolution matrix or create convolution filter essentially matrix using a polynomial of each of these, it is going to be commutative with respect to the other one as well. So now, so far, we looked at convolution in the nodal space.